Okay, at this point, right, we should all be ready to go with our Lewis structures. We understand how to draw Lewis structures, and we are going to start moving into the idea of molecular shapes, also known as molecular geometry. Although when I say that, I know a lot of people get the chills. They're like, oh, geometry, now we're really going to start doing a lot of math. And that's really not what we're talking about. We're simply just talking about shapes. How do we determine what the shape of a molecule is? Well, there's a couple of things that go into it. One of the first things that you have to realize is that if you're going to start causing nonmetals to come together to share their electrons, they're going to have to start overlapping with each other. And if you overlap atoms, and atoms have atomic orbitals in them, then those atomic orbitals eventually are going to start to overlap. And when they do, they form molecular orbitals. Now, there's a lot more information that goes into what a molecular orbital looks like and how it works. And there's a lot of information I don't think is going to be necessary for us. Even your book has quite a bit in it that we don't really need to know all of that to start exploring this idea of shapes. So the key here is I just want you to understand what the basic definition of a molecular orbital is. Molecular orbital is when atomic orbitals from different atoms overlap, right? And then they change into what we call molecular orbitals. The molecular orbitals are partially responsible for the shape. The other part that's responsible for the shape is a theory we call the Vesper theory, okay? The VSEPR theory. So the Lewis structures we've been drawing are obviously only two-dimensional, right? Because you're putting them down on a piece of paper. You're not creating a three-dimensional model of any kind, and it doesn't show any sort of shape. In fact, I've been really lax about where to put different parts in the Lewis structure. You know, if we said, okay, so-and-so goes in the center, and these other ones go around the outside, where do you want to put them around the outside? And it doesn't really matter. Well, it does to a certain degree. Okay, and that's what we need to start getting into is a little bit more detail about where we put everything in our Lewis structures. Now, all of that is going to be kind of governed by the idea that electrons are negative and they repel each other, right? Because negatives repel other negatives. They push them away. And so if you have all of these different pairs of electrons in an atom, all these pairs of electrons don't want to be near each other. They want to push each other as far apart as possible. So we get this theory, VSEPR, the Vesper theory, which stands for valence shell, electron pair, repulsion. Now you know what all of those words mean. Okay, let's break them down. Valence shell, so that's the outermost part of the atom, the outermost electron shell. Electron pair, a pair of electrons. And repulsion, which means that the electrons are pushing each other away. So this simply says that the pairs of electrons that exist on the outer edge of an atom repel each other. They push each other away. So the three-dimensional shape of a molecule is determined how far the electron pairs are apart from each other, right? Because they're going to be pushing each other away. So let's take water as our example. Now, water is H2O. If I went through and I did all of the steps of coming up with a Lewis structure, right? I would add up all of the valence electrons that are in two H's and an O. So an O is in group 16, so it has 6, and H is in group 1. There's 2 of them, so 2 plus 6 makes 8. So I have 8 valence electrons to work with. The O has to go in the middle. Why? Because H's can never go in the middle. I put one single bond in between each, and then I start putting lone pairs everywhere except for H's, right? So now, is the O happy? Well, it has 8, so it's good. Is the H happy? Well, it has 2, it's good. And this H has 2, it's good. And total, did I use the 8 that I started with? Yes, 2, 4, 6, 8. Now, I drew it like this because up to this point we said it didn't matter where I put the H's. But it turns out it does, right? A water molecule does not look like that in real life. It is not straight across like that. And it turns out because of these lone pairs actually take up a lot of space. We draw them as these tiny little dots, but it turns out that they take up a lot of space. And so a water molecule actually looks like that. All right, it looks like that. It is this bent shape. And the reason why is because each of these lone pairs here is pushing the other away. And that means that these H's that are trying to hold on get pushed down and out of the way. So I drew these in not because that's how you should draw them. That's not why they're there. I simply draw these in because I want you to realize that there is sort of an invisible area where these lone pairs want to fill in, right? They want to take up that space. And so that's why they're pushing those H's out of the way. Right? There's a certain bond angle that occurs between the H's. Now, we're not going to get that specific in here. We don't have to worry about memorizing bond angles or anything like that. But I do want you to start to get used to the idea that there are names for these shapes. And a water molecule is a bent shape. Now, this is how we draw our Lewis structures, right? We draw our Lewis structures with sticks and little dots and that kind of thing. But there are obviously more realistic ways that we could portray the water molecule. Right, here's a water molecule showing the actual shells, the actual energy levels where the electrons are. So here are the two that are being shared between this hydrogen and this oxygen. Here are the two that are being shared between this hydrogen and oxygen. Here's this lone pair. Here's this lone pair. And you can see how these lone pairs are taking up their own space, and they end up pushing the shared ones out of the way. By the way, if you were to take this whole shape here and you were to kind of turn it just a little bit, you can see it kind of looks like Mickey Mouse. In fact, a lot of people describe a water molecule as a Mickey Mouse molecule. Probably an even more realistic model of what a water molecule would look like would be that. Right? That's a really realistic view of a water molecule. Why? Not because oxygens are red or anything like that, or hydrogens are white, but because this is showing what you would probably really see if you could see the atoms. The atoms are just going to be these spheres, and they're overlapping with each other. But there still is this bent shape. Now, to draw this would require a lot of artistic talent, which most of us don't have, right? So in here, we stick with Lewis structures, right? We're basically drawing stick models. And I know that sounds really crude, and you're like, but I love to draw. Well, that's great, but not everybody can do that, so that's why we stick with simple models, like we do for the Lewis structures here. Now, there are a lot of different kinds of shapes. Right? Bent is just one of many different shapes that are possible out there. And so for all of these shapes, what we need to do is determine when to draw them and how to draw three-dimensional shapes using a two-dimensional technique like stick models, right? So we're going to have to get a little bit creative in how we're going to do this. And so the idea is that at this point, we're going to start to explore together in class. And then I'll go over a way that we can determine the shapes without having to do anything too dramatic.